Good evening, everyone. Welcome to the week 8 live interaction session, the last live interaction session for the course Waste to Energy Conversion. So, as usual, let's just wait for a minute or so before we begin our session for today. So, let's start our session for today. Let me just share my screen. I hope I'm audible. Yeah. So, I welcome you all to the week 8 live interaction session for this course Waste to Energy Conversion. This course is offered by Professor Prasenjit Mondal sir from the Department of Chemical Engineering, IIT Roorkee, Uttarakhand. This course is offered by the NPTEL SWAYAM program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. I am responsible for conducting live interaction session for this course for the Jan to May 2026 semester. So this is the last live interaction session for this course, that is the week 8. So just a second. Yeah. So so far we have traversed across 7 live interaction sessions, and the 7 week of the course has already been completed, and I hope that you all of you had also gone through the week 8 lecture contents. So till now, we have discussed about waste to energy conversion as such, on the advantages of waste to energy conversion. Then we discussed about the different types of uh, ways or routes for the conversion of waste to energy, starting from thermal and then biological conversion routes. In thermal conversion routes, we looked at 3 different types. One is the pyrolysis, gasification, and then another one is incineration, or also known as combustion. So we discussed their principles and what differentiates each one of them, and what kind of gases, or you can say what kind of products do we obtain from each of this thermal conversion process, and how each of this each of the process that we discussed are useful in the industrial scale, used for industrial applications. So after that we also discussed about the energy production from fermentation, energy production from plastic waste, energy production from trans-esterification reactions, and today we will discuss about the energy production from algal biomass. So we are constantly discussing about how to convert waste to energy so that the waste management system becomes more efficient, so less waste gets accumulated within the environment to make the environment a better place. And it's not just about minimizing the waste but also trying to extract something useful out of the waste material. So that is the objective of the course. So as far as today's course's lecture content is concerned, it's about the wastewater treatment and energy production from the algal biomass. So if you see, algal biomass is something that usually you can see which grows in stagnant water, and by using algae we can actually produce energy. And the major advantages of using algal biomass for energy production is that the waste actually gets minimized, and the entire process is going to be carbon neutral, so whatever the amount of carbon that gets generated will be used up in the process. And then the third advantage is going to be that in the process of converting this algal biomass to get energy, you are also going to do a wastewater treatment. So the water that is you are going to use, or from where you are going to collect this biomass, gets treated. So that is typically the major advantages of this algal, of using algal as a biomass for the energy production. So there are different ways of, so depending upon the type of algae that you use, you have different classes of algae. So based on the type of algae, the energy production routes may vary. So that's what is covered in the lecture contents, and I hope you all have gone through the lectures. So now let's get directly into, without much on the course content, since we are in the last, today is the last live interaction session. So let's get directly into the questions. So which of the following is not an example of saturated fatty acid? Is it capric acid, lauric acid, or linoleic acid, or none of the above? Option C, linoleic acid. Okay. So do everyone agree with that? That linoleic acid is not an example of saturated fatty acid? I hope everybody has an understanding on what is saturation. Like in a in case of a carbon based compound, what exactly saturation and unsaturation means, that distinction everyone is clear. I hope everyone is clear. So saturated carbon compounds or saturated fatty acid is the one which do not have any kind of double bonds present in them. All the bonds that are going to be present in the compound is a is a sigma bond. There is no pi bonds, or you can say there is only one single bond between the two molecules. There is no double bond. Whereas in case of the unsaturated fatty acids, you are going to have double bonds present within the carbon chain. So one of you have told linoleic acid is not an example of saturated. So that means linoleic acid is an unsaturated fatty acid. Any more response for this one? Anyone else? Linoleic acid. So let's look at the table. Let me just show this. Oh, just a second. Yes. So if you see from this table, you have different types of fatty acids, and they are categorized as saturated fatty acid and unsaturated fatty acids. So if you see in case of saturated fatty acids, you have examples like capric, lauric. When I say capric fatty acid, lauric fatty acid, myristic fatty acid, palmitic, stearic, acadic, behinic, and lignoceric. Whereas in case of unsaturated fatty acid, that is which basically has a double bond or a triple bond present in the carbon chain, you have myrstolic acid, palmitoleic acid, sapienic acid, hexadodecadienoic acid. So many of them, oleic and linoleic and alpha linoleic. So linoleic is the correct answer. And if you see in case of the linoleic acid in the carbon chain, you have two double bonds present in them. So their degree of unsaturation is going to be 2, and they are an example of unsaturated fatty acids. Whereas if you see capric and lauric, they do not have any kind of double bonds in their carbon chain. All the bonds that are going to be present in them are sigma bonds. So they come under the class of saturated fatty acids. So this is correct. Linoleic acid is not an example of saturated fatty acids. So let's move on towards the next question. The question is, which of the following is used as a chemical flocculant to harvest algae? Is it ammonium chloride, calcium chloride, ferric chloride, or none of the above? Chemical flocculant. So what's a flocculant? Which of the following is used as a chemical flocculant to harvest algae? Ferric chloride, someone is told. Okay. But what is a flocculant? Okay, let this be an let me not mark it then. Okay. What is a flocculant? I mean, first, what is mean by a flocculant? Then we will see the answer. So flocculant is something that basically helps the process of flocculation. It basically, flocculant is the one that basically makes the flocculation process happen. So what is flocculation? Flocculation process definition. So flocculation is nothing but it's a process where the colloids actually comes out of the solution, or you can say it comes out of the suspension in the form of flakes, and then you can actually yeah, that is the process of flocculation. So flocculation is nothing but it's basically a process where the colloids comes out from the suspension in the form of flocks or flakes, whatever you call it as. So a flocculant is the one that helps the flocculation process and aids in the formation of the flakes. So this algae, whenever it is going to float in the water, major problem that happens with the physical methods are that they are not very efficient. So when we do it physically, when we try to harvest these algae from the wastewater physically, there are chances that majority of the algae may remain within the water, and you cannot actually extract the algae in a very efficient way. So the efficiency of the process, of the physical process for harvesting the algae is very less. So in order to make sure that almost all the algae comes out of the water, we are able to harvest almost 100 percentage of the algae from the water, and then basically clean the water. For that we use chemical flocculants. So there are two types of chemical flocculants. One thing is called as an alum, and second thing is the ferric chloride. So when you add them to the water, what it does is it collects all the algae from the suspension and then settle down at the bottom as flakes. Then you can easily collect those sediments or the flakes at the bottom of the water, and by this you can harvest more amount of algae, and at the same time the water that you are actually going to clean becomes more the water that you are supposed to do treatment gets more clean. So using a chemical process for harvesting the algae is much beneficial. So one thing is the ferric chloride, and another thing is the alum. So these are the two chemical flocculants that I use. So the chemical formula for alum is K2SO4 dot Al2SO4 thrice dot 24H2O. And I hope ferric chloride, I hope everyone know the chemical formula. It is FeCl3. So this is the way to harvest the algae. So once the algae gets harvested, you can actually go for using this algae as a raw material for energy generation. Now let's come to the next question. So this is something related to trans esterification process. Which of the following are Catalyze, or which of the following are catalyzed transesterification process? Or you can say which of the following falls under the category of catalyzed transesterification process? Is it homogeneous base catalyzed, or homogeneous acid catalyst, or it is enzyme catalyzed, or all of the above? We discussed this in the last live interaction session. I mean, in the course 7, week 7 of the course, where we saw that for the transesterification process to happen, you need a catalyst, and then you also need to supply some amount of heat to basically generate glycerin. So the question is, which of the following is or are catalyzed transesterification process? Is it homogeneous base catalyzed, or homogeneous acid catalyzed, or enzyme catalyzed, or all of the above? And of course, please provide few examples for each of the for the correct answer that you think. You also need to state what are some of the examples of, let's say the answer is homogeneous base catalyst, then you need to provide me examples of the same. Yes, which of the following is our catalyzed transesterification process? Homogeneous base, homogeneous acid, enzyme, all of the above. Oh, enzyme catalyst. Yes. So, Mr. Sivakumar, yes, your answer is correct. So, for the chemical flocculants, but for the catalyzed transesterification process, you're saying the answer is C, enzyme catalyst. But what about option A and option B? Are they wrong? Or if they are wrong, then why do you think so? If you happen to, okay, yeah, okay. So all of the above, okay. So I hope all of you are able to remember the transesterification reaction that we discussed in the last session. So over there, if you see, we have written that this transesterification process happens only if you use a catalyst. Only then you can actually obtain glycerin, or otherwise it is not possible to actually form glycerin from the triglycerides. So you need a catalyst for the transesterification process to happen. So in this case it is written that which of the following are catalyzed transesterification process. So as such, for a transesterification process you can use base as a catalyst, you can use acid also as a catalyst, and you can use enzymes also as a catalyst. So for this question, all the above is the correct option. Now, so I hope everybody agree with the same. Anyone who is like not able to get why it is all of the above? So, so please provide few examples for each of the options. Like for a homogeneous base catalyst, provide some example. For homogeneous acid catalyst, provide some example. And for enzyme catalyst, please provide some examples. Just one or two for each will be sufficient. I think for homogeneous base, it is simple. So this we discussed in the last week content itself. So for homogeneous base, it would be sodium hydroxide or potassium hydroxide. What about for homogeneous acid catalyst and enzyme catalyst? Any of the response? And also we discussed this, that what happens if the concentration of sodium hydroxide and potassium hydroxide is more. Examples for a homogeneous acid catalyst. It will be sulfuric acid or hydrochloric acid. For enzyme catalyst, any idea, any guesses on what kind of enzymes could be used for this trans-esterification process? So I'll just mention it here, but have a look at the examples as well for when you read about transesterification process and the different types of catalyzed transesterification process as base, acid and enzyme. Kindly have a look at few of the catalysts which are used in each of the process. So for enzyme catalyst, it is lipozyme, 60, and next one is novozyme 435, and some lipids also can be used for the enzyme catalyst transesterification process. So kindly have a look at the examples as well. So sometime they may be helpful. So in relation to this question, let's look at the next one. Give given three different routes for transesterification reaction: base catalyst, acid catalyst, and enzyme catalyst. Comment on the rate of reaction and explain. So basically I'm asking which one will be more faster compared to the other, or what is the order of the rate of reaction. Is it, which one will progress more faster and which one will be slower? And so the major reason why we use a catalyst is to basically make sure that the rate of reaction is enhanced. But depending upon the type of catalyst that we use, this rate can actually vary. So we want to know which one will be more faster. Is it by base catalyst, or acid catalyzed, or enzyme catalyzed? Any guesses on which one could be? Or let me give out the answer. You guys can try to explain me why the rate of reaction is in the following order. I think that would be. Oh, we have an answer. No, the question is, so I think there is some. So the question is, there are three different types of esterification process we are discussing, right? Base, acid, and enzyme. Different types of catalyst. So as I said, catalyst is the one which helps in making sure that the chemical reaction proceeds at a faster rate. But depending upon the type of catalyst that you do, the rate may vary. So my question here, what I want to know is, Which among the following, base catalyst or acid catalyst or enzyme catalyst, makes the reaction proceed faster? So if I use, let's say for example, if I use sodium hydroxide, will my transesterification reaction process happen faster? Or if I use H2SO4, then will that transesterification process happen faster? Or let's say if I use lipozyme IM60, will my transesterification rate will be faster? So if there will be a order, I mean ascending or descending order. So let me give out the answer. I think some of you can help me explain why this order is observed. So base catalyzed is greater than acid catalyzed than enzyme. So this is the order. So if you use base as a catalyst, then the pace at which the reaction progress will be faster compared to if you use acid, compared to if you use enzyme. So now please explain me why this order is getting followed. What could be the reason behind this order? So if you just want to look at this table, oh, so if you see the rate of reaction or reaction rate in base catalyst is far higher or is more compared to acid catalyzed compared to enzyme catalyzed transesterification reaction. Now the question is, why is it so? Any idea? Again, base, if you see, it has its own limitation, because if the free fatty acid is going to be present and it's going to be present in excess, then they may react with the sodium hydroxide or potassium hydroxide to form soap, and I mean to form more soap. So the formation of more soap will affect the quality of the glycerin that you will get. So the biodiesel's quality that you are going to obtain at the end of the transesterification process is going to be low. So that will degrade the energy density of the fuel. So overall quality of the fuel will be affected if you are going to use base catalyst. There are chances of that is more compared to acid or enzyme catalyst. This is what we discussed in the last session also. Now, why is that particular order is? Have a look at it. Let's see towards the end. So I'm going to leave it here. So let's see about this question. Next question. Oxidation of bio oil takes place due to saturation, unsaturation, both A and B, none of the above. Oxidation of bio oil. The key word to this answer lies in the word oxidation. Can saturated fatty acids or saturated carbon compounds undergo oxidation easily? Or which one will undergo oxidation more easily? Unsaturated or saturated? So it's going to be, any response do I have? Okay, no one. It's going to be unsaturation. So when you try to oxidize the unsaturated carbon compounds, what's going to happen is it is going to get it's going to get converted to saturated fatty acids, and then it's going to release the electrons. So that's what is an oxidation process. In case of oxidation, it is defined as a process wherein electrons are lost. So for this question, oxidation of bio oil takes place due to the unsaturation that is present in the molecule, or you can say the fatty acid or the bio oil. Next question, which of the following is a natural antioxidant used for increasing the stability of the biodiesel? So remember the word natural antioxidant. Is it tocopherol or pyrrolgalol or propyl gallate? which so all these are antioxidants, and they will help in improving the stability of biodiesel. The question is, among the three, which of the following is a natural antioxidant? The other two are synthetic. Is it tocopherol, pyrogalol, or propyl gallate? Two of them are synthetic and one is natural. Any answers? Oh, uh, is my screen visible to everyone? Or just a second, let me stop sharing and let me share my screen once again. Huh. Okay. Is my screen visible now? Anyone? Oh, um, okay, yes, fine, okay. So, which of the following is and first of all, why do we need to add? So, yes, we need to add antioxidants so that the stability of the biodiesel can be maintained. But suppose, let's say, if we don't add an antioxidant, then what will happen to the biodiesel, or how it will affect the biodiesel? Let me put the question somewhere here. How absence of antioxidant affect the biodiesel quality, or you can say affect the quality of the biodiesel. Just let me. I mean, we can think about a case wherein if we don't use an antioxidant, the biodiesel may get oxidized. Okay, so what problems will arise if the biodiesel is going to oxidize? Does that mean my energy density will reduce? Okay, try to find out the answer for this one, like any sort of guesses. You are welcome to tell me now or try to find out the answer. Increase the life. Okay, so majorly we use an antioxidant so that the biodiesel's life is increased. Okay, apart from that, any other reasons? I'll mark one as here. Let's remove none of the option above option, because as I said, increase the life. Any other reason that you can think of? Just think about it. Okay, now let's first finish this question. Which of the following is a natural antioxidant? So I'll give a clue. So this one is synthetic. Pyrogalol is a synthetic chemical, so that can be used as an antioxidant. Just a second, let me put this in the next slide. So think about this. Let's see this one. Oh, oh no, this one. So third one was none of the above, but so pyrogalol is synthetic and propyl gallate is also synthetic. So it is only the tocopherol which is natural, and this is something that is vitamin E, has tocopherol in it. So please try to remember this. So the answer is tocopherol, which is a natural antioxidant that is used to increase the stability of the biodiesel. So next question, identify the most appropriate option that explains the major challenges for microalgae. Is it the high cost of oil extraction, or is it basically defining a cost effective bioreactor, or is it about finding a suitable strain for microalgae, or is it all of the above? So as I said previously itself, the algae are have different varieties in them. So there are different varieties of algae, different strains of algae. Depending upon the type of strain, the energy production, or you can say the extraction of energy, will be different. So here you have to let me know among the three options or four options, which one of the following is the major challenge for microalgae harvesting, you can say, or major challenges for production of energy from microalgae. Just a second. Okay. So it's going to be any responses there from anyone? Improve. So all of the following are the major challenges for the microalgae harvesting. High cost, designing an effective bioreactor so that you can maximize the oil extraction production, and to find a suitable strain that helps in getting more oil. All of the following are the major challenges for the microalgae energy harvesting. So let's move on towards the next question. Identify the following photobioreactor. Is it vertical column or horizontal tubular or flat panel or none of the above? So there are three different types of photobioreactors, right? Vertical column, horizontal column, and flat panel. So which of the following is the photobioreactor that is shown in the picture? So which one of the following is this bioreactor? Is it a vertical column or a horizontal tubular or a flat panel? So okay, no one. So this is a flat panel photobioreactor. So next question is, among the homogeneous catalyst and the heterogeneous catalyst transistification reaction, which process according to you could be the best for the generation of biodiesel from algae? So what, I mean, among both homogeneous and heterogeneous, which process could be the best and why? So what are the factors that we need to consider for a process for to basically determine which one will be useful or which one will be best? Just the factors. Even if you're not able to basically come up with the answer, what could be the factors that we need to consider to basically say whether the process is, which of the two process among homogeneous or heterogeneous is the best? So I'll just list the process here. You can let me know which one of the following is better as per the factors that I've listed. So the first one is the conversion rate. Second one is post treatment step. After that, you have processing methodology, and then you have the presence of FFA. FFA is nothing but free fatty acids, and then you have catalyst reuse, and then you have cost. So based on all these parameters, we need to analyze which of the transjustification, homogeneous catalyst or heterogeneous catalyst, is best for the biodiesel production from algae. Any So based on these we need to see. So take this as a task and then try to identify which one will be correct among the homogeneous, I mean which one of the following will be best among the homogeneous or the heterogeneous catalyzed transesterification reaction for the production of biodiesel from algae. So when you are going to try, when you are trying to say a process is best or not, you need to consider certain factors. It's like how you take personal decisions as well, right? So if you're supposed to, let's say, purchase a particular thing, and then if you have two choices, you will always list out the factors which factors that are common, and then based on those factors you try to identify which one will be best for you. So depending upon the cost and various other factors, you actually make the decision. Similarly, here also, for the production of biodiesel from algae, we have two processes, homogeneous and heterogeneous catalyst transesterification reaction. We need to we need to identify which one will be the best, and for that we list out 6 different factors. So based on these factors, we need to identify which one will be the best. So, I think, yeah. So here we end our discussion on multi-choice questions. So, if you have any doubts, please let me know, or otherwise we can progress towards the numerical problems. Any questions? Anyone? Okay, if no doubts, then let's move on towards a numerical problem. Let me just switch one. Ah, yeah. So this is for today's session. So let's first start with this question. So yeah, bio oil extracted from an oil seed sample. Its sample has 80% triglycerides containing 3 long chains, which can produce methyl esters of lauric acid, myristic acid, and palmitic acid in equimolar ratio or equal molar ratio during the transesterification using methanol and the sodium hydroxide catalyst. Calculate the amount of biodiesel produced by the transesterification reaction of 20 kgs of bio-oil. Assume that the efficiency of the conversion is 90% and 10% of palmitic acid is converted to soap. Calculate how much glycerol will be produced and how much soap is formed. So take some time, 2-3 minutes, and then try to find out the answer, or at least the steps for calculating how much glycerol and soap will be formed in this process. Oh, Sorry, there was a network connectivity issue. So let me just share my screen again. So this is the question. I hope my call got disconnected when I completed the question. Let me just describe the problem once again. So bio-oil extracted from an oilseed sample has 80% triglycerides and it contains three long-chain fatty acids. One is the methyl esters of lauric acid, another one is methyl esters of mystric and palmitic acid, and all of them are going to be present in the equimolar ratio, and the trans-esterification process happens in these three fatty acids using methanol and sodium hydroxide as a catalyst. Now we need to calculate the amount of biodiesel that gets produced by the trans-esterification of 20 kgs of the bio oil. Assume that the efficiency of the conversion is 90% and palmitic acid's 10% is going to convert as soap. We need to calculate how much glycerol will be formed and how much soap will be formed. So let me just give the molecular weights because I think that will be a bit. So the molecular weight of each compound that I'll give now. So the first one is lauric acid, and please be careful here. It says methyl esters of lauric acid. So the formula will be changed. So For the first one, so let me just write methyl ester of lauric acid. It's going to be, formula is going to be CH3 CH2 10 COOCH3. Similarly, for the mystric acid, it's going to be, just let me copy, myristic acid is going to be CH3 CH2 12 COOCH3. And similarly, methyl esters of palmitic is going to be CH3 CH2 14 times COOCH3. Now for this we need to calculate the molecular weight. So just a second, for each one of them I have calculated it previously. So for methyl esters of lauric acid, it's going to be 214 gram per mole. For myristic acid, it's going to be 242 gram per mole. And for palmitic acid, molecular weight is going to be 270 gram per mole. So please check the calculation once. And I'll also give what will be for glycerol. So glycerol formula is CH2 twice CH OH thrice, and its molecular weight is going to be 92 gram per mole. So with this you need to calculate how much glycerol will be produced and how much soap will be formed. Anyone with any answers till now, or I hope the screen is visible, right? So what will be the bio oil, the molecular formula for the bio oil? So that also let me give it. Molecular weight of triglycerides is, the formula will be something like this. and the molecular weight is going to be 722 gram per mole. Please calculate along with me and let me know if there are any errors. So all these calculations I did previously because these will consume a lot of time. So please check the values before you solve the problem. So I think the answer is correct, 722 gram per mole. Now all the molecular formula is known and we know the reaction that triglyceride plus alcohol in the presence of NaOH or whatever that base as a catalyst will give glycerol plus soap. Now with this reaction you need to calculate how much glycerol and how much soap will be used if this is the triglyceride and 80 percentage of the triglyceride is what is used for the transesterification reaction and we are given that 20 kg of the bio oil will be used, and in this 20 kg 80 percentage is triglyceride. This part was a tedious part so I have given out now, so try to solve it and let me know the value. We will start solving it within a minute or so. Let me keep this. So I think I need an extra slide. So the basis is given as 20 kg of bio oil and we are given that 80 percentage of the bio oil is made of glycerides or 80 percentage is triglycerides are present. So now since we know that 20 kg of bio oil is there and 80 percentage of it is going to be triglyceride, then mass of triglycerides in the in bio oil will be 20 times 0.8, so that will be 16 kg. So in 20 kg, 80% is triglyceride. So if you try to calculate the mass of triglyceride in the bio oil, it's going to be 16 kg. Now we need to calculate the moles of triglyceride in bio oil. So we know it is 16 kg. That is that. So number of moles is given weight by molecular weight. Molecular weight we calculated it as 722 grams, and mass of the triglyceride in bio oil is going to be 16 kg. So if we convert kg to grams, it will be 16,000 grams by 722. So the value is 22.16 gram per mole. Oh, sorry, 22.16 moles. Now we know the moles of triglyceride in bio oil. So once you know this, you can actually calculate the moles of glycerin, moles of glycerol, and once you know moles of glycerol, then you can calculate the weight of glycerol. Once you know that, you can calculate the weight of the triglyceride and the soap that is formed. So moles of glycerol will be, since the stoichiometric coefficient is 1, so whatever the moles of triglyceride is there, that only it will be, you will get in the glycerin as well. So it's going to be 22.16 times 92. So what is the value? 2038.72 grams, or you can say it as 2.038 kg of glycerol will be produced through the transesterification reaction. Once that is done, now we need to calculate how much soap is going to be formed, right? So it is given that 10 percentage of the palmitic acid is going to be converted into soap. So moles of soap, or amount of soap formed, is equal to 0.1, that is 10 percentage is 0.1 of the palmitic acid. So 22.16 times the palmitic acid's weight, that is 270. So which will be nothing but 0.1 times 270 times 22.16, 598.32 grams of soap is produced. Is this fine? This is the answer. How much more? How much? Sorry. This should be the amount of glycerol, and this is the amount of soap that is formed. Is this fine? I mean, Whether all of you are getting the same answer or any different answers. Any different answers or any doubts. I hope everybody is able to understand. We just calculated the molecular weight of each of the following uh, reactant and the product that will be a part of this reaction. Once that was done, we had the data that 20 kg of bio oil is being used for the transesterification process, and out of that 80% is triglycerides. Since we know that only triglycerides can aid is the raw material for the formation of glycerol and soap. So we calculated what is the mass of triglyceride. Once we come to know what is the mass of triglyceride, we calculated the moles. That came out as 22.16 moles. Once we know the number of moles, we know that for every 1 mole of triglyceride that is reacting with the alcohol, we are going to get 1 mole of soap and 1 mole of glycerol. So that means so for every 1 mole of glycerol reacting, you are going to sorry, for every 1 mole of triglycerides reacting, you are going to get 1 mole of glycerol. That means for 22.16 moles of triglyceride that is reacting, we are going to get 22.16 moles of glycerol. So that means the amount of glycerol that will be produced is 22.16 times its molecular weight, which is 92. That turns out here as 2038.72 grams or 2.038 kgs of glycerol. Next, when we come to soap, it is written that 10% of the palmitic acid is going to be converted. So the number of moles of palmitic acid is 22.16 moles. That times 217 will give you the weight of palmitic acid, and 10% of that will be contributed to the soap formulation. So that comes out as 598.32. Is this fine? But I say these answers are not correct. There is a mistake in the answer. There is a factor that we are forgetting in calculating the glycerol amount and soap that gets formed. A small mistake is there. So let me show you the question. I hope you will be able to find out the mistake. So please read the question and then let me know what is the error. There is the error with the answer. Anyone, any guesses what could be the error? It's a minor error. There is a factor that we are missing. So it says that assume the efficiency of the conversion is 90%. But as far as the answer that we wrote here, or the what we solved and got, we didn't account for that 90% conversion. We what we wrote here is for 100% conversion efficiency. When I told 1 mole of triglyceride reacts to produce 1 mole of glycerol, I assume that the conversion efficiency is 100%. But the question says conversion efficiency as 90 percentage. So we need to do some small modification here. So now the answer get rephrased as for every 1 mole of triglycerides we are going to get zero point 0.9 mole of glycerol as per the question, which states that the conversion efficiency is 90 percentage. So that means for 22.16 moles of triglyceride that is reacting, you are going to get zero point 0.9 times 22.16 moles of moles of glycerol. So I need to add a step here. Amount of glycerol formed is going to be 22.16 times zero point 0.9, and why that zero point 0.9 is because is factor is due to the conversion efficiency being 90% as stated in the question. So please keep in mind of these kind of small things that can actually trick us in not getting the correct answer. So if this is the moles of glycerol that is formed, then the amount of glycerol you actually need to add a zero point 0.9 factor here. So then the value will be zero point 0.9 times 22.16 times 92, 1834.84. 84, that is 1.834 kb. Similarly, even for the soap also you need to multiply a factor of zero point 0.9. So that is going to be 598.32 times zero point 0.9. 538.488. So this much. So these many grams of glycerol and these many grams of soap will be produced by the following transesterification reaction. Any questions? Anyone, or shall we progress towards the next one? So if you have any question, then please let me know. For those who do not have any question, yeah, start have a look at the second problem. 100 ml bio oil sample is reacted with 90 grams of iodide monochloride ICl. After reaction, Ki is added and liberated iodine is titrated with the sodium thiosulfate. If zero point 0.3 mole of sodium thiosulfate is consumed to reach the titer value, determine the iodine value of the bio oil. I hope all of you remember the concept of iodine value. This is something that we discussed while talking about the characteristics of bio oil, that is cloud point, pour point. I also asked one question, if I remember correctly, which temperature will be lower, or which of the following will occur at a higher temperature? Is it the cloud point or is it the pour point? So if you remember that concept, there we discussed about the iodine value. So the question is, 100 ml bio oil is going to react with 90 grams of iodide monochloride. After the reaction, KI is added, potassium iodide, and a liberated iodine is titrated with the sodium thiosulfate. 0.3 mole of sodium thiosulfate is required to achieve the titer value. Determine the iodine value of the oil. So we approximately have 10 to 15 minutes. So let's try to solve this problem and this one. So what will be the reactions for this? You will have two reactions. That's how you'll be able to calculate how much will be the iodine value. So let me give out the reactions here. So the reaction is as per the question. ICl reacts with Ki to form KCl and liberates iodine I2. This iodine then reacts with sodium thiosulfate. Formula is Na2S2O3. And then that gives sodium iodide plus Na2S4O6. So this is the reaction. Now I think we need to balance this. So I think the first one is 2 IC, or wait. So first one is as it is. Second one should be 2, if this is 2 Na, 4 Na. So here also 4, 4, 4. Yeah. So now the reaction is perfect. So this is the reaction. Now it is told that for 0.3 mole of sodium like the liberated iodine consumes 0.3 moles of sodium thiosulfate. Based on this, we need to do the back calculation to identify what is the iodine value of the oil. So 0.3 moles of sodium thiosulfate is consumed. So as per the equation, if you see, for every 1 mole of I2, 2 moles of sodium thiosulfate is consumed. As per reaction 2, 1 mole of, sorry, for 1 mole of I2, 2 moles of Na2S2O3 is consumed. So then for zero point 0.3 moles of Na2S2O3, how many moles of I2 will be consumed? So the answer will be 0.15. I hope this is not difficult. For 1 mole, you have to, for 1 mole of I2, 2 moles of Na2SO4 3 is consumed. If 0.3 moles of sodium thiosulfate is consumed, then how many moles of I2 will be there? So that is 0.3 by 2, which is 0.15 moles of I2. Now, what will be the molecular weight of 0.15 moles of I2? Just a second. I2's molecular weight is 253.8 a gram per mole. So that will be 30, just a second, 0.15 times 253.8. What it will be? 38.07 grams of I2. Now it is written that 100 ml of bio oil is reacted with 90 grams of iodide monochloride. So how much I2 will be produced within the reaction? So we can see from here that for 1 mole of ICl, 1 mole of Ki is produced, or 1 mole of Ki is consumed. So 90 grams of ICL is going to be reacted. So then the number of moles of ICL will be 90 by molecular weight of ICL is 162.35. So that would be 0.554 moles. So then how to proceed? What will be the amount of I2 that is released in the reaction? That is also going to be 0.554 moles. Yes, is it fine? Is it fine? So then this value will be around 70.34. I have already calculated it, so please check it once again if there is any calculation error. So the difference is nothing but 70.34 minus 38.07 grams. So that is nothing but 32.27 grams of I2 in 100 ml of bio oil. Okay. So the iodine value will be 32. Iodine value is nothing but the amount of I2 gets that remains as an excess in the given volume of the bio oil, or you can say in 100 ml of bio oil. That is what is the iodine value of the oil. So if you see here, 70.34 grams of iodine is getting liberated, but then the amount that is getting consumed for the treatment with the sodium thiosulfate is going to be only 38.07. So the difference is the iodine value. Is there any questions? So if no questions, then let's see this question once. This is a very simple one. So 100 kg of waste cooking oil was fully dissolved in some amount of neutralized ethanol by heating and titrated with the N by 10, that is zero point 0.1 molar KOH using phenolphthalein indicator. If the titer value is going to be 120, calculate the acid value. I hope all of you know how to calculate the acid value S. The equation that we discussed, I think, in the last live interaction session, or probably in week 6. Let me just give out the expression. I hope after that is it's just about calculation. S is equal to 56.1 times V times C by M. So S will be nothing but 56.1 times V, that is 120, times C. Here it's written n by 10, which is nothing but zero point 0.1, divided by mass, that is 100. So if you do, it should be 56.1 times, let me just calculate the value. 6.372. 6.732, sorry. And as we discussed, this is a dimensionless quantity. So the S value is going to be just 6.732. So this is just a two line problem. So once you know the formula, then it's just about substitutions. Just be careful, n by 10 means zero point 0.1 molar, zero point 0.1 normal KOH. Any questions related to the three problems that we discussed today? So let me just stop sharing the screen. If you have any doubts, then you can raise your questions. So we will have a live interaction session tomorrow. So that will be mostly from 6 to 8 p.m. and you will get a notification for the same. I think hopefully by tomorrow you will get. So if you have, so we will discuss the rest of the problems and including like some sort of a revision of all the 8 weeks course content in the next that would be the last live interaction session. So if you have any doubts, you're welcome to let me know now, or I think we can conclude our session today. So if you have no doubts, I think we can conclude our session. So thank you all for joining today's live interaction session. So this live interaction session is getting recorded and it will be there in the YouTube very soon. So the link will be provided to you, so you can access the link through the course page. I hope all of you are able to do the same. So the presentation will also be uploaded along with the video, and I take this as an opportunity to thank Professor Prasenjit Mondal sir as well as the NPTEL team for providing me this opportunity to interact with you all in the Sunday afternoon from 5 p.m. to 7 p.m. So our last live interaction session will be on 16th of March from 6 p.m. to 8 p.m. So till then, if you have any questions, you are welcome to email me or post it in the Q&A session, and I will see if there are any questions. Then I'll be able to respond to that also as soon as possible. So yeah, Thank you for joining today's session, and have a great weekend ahead and a week. Have a great weekend and a week ahead. Thank you and bye.